Welcome everyone to this week's IAMP Mathematical Physics seminar. For those of you who are new to this, this is the regular seminar of the International Association of Mathematical Physics. So if you want to follow the seminar series, there is information, there will be information in the chat. And if you want to find out more about IAMP and maybe become a member, please go to our website and read more about it. But now it's time for the talk. So it's my great pleasure today to introduce Kevin Costello, who is based at the Perimeter Institute of Theoretical Physics in Waterloo, Ontario, and he's going to talk about Vertex algebras and self-dual Yang-Mills theory. This talk is going to be recorded, and you can watch or rewatch it on YouTube later in our YouTube channel. Kevin, please take it from here. Thank you.
Okay, thank you very much, Kaja. It's a great honor to be invited to speak in this seminar series. So what I'm going to talk about is, so everything is joined with Natalie Paquette at the University of Washington. So I'd also like to ask the audience to please interrupt and ask questions as we go, because I'm not entirely sure of the background and interests of the audience members. So I'm not quite sure my talk is calibrated to the right audience. Like I gave the same talk yesterday to a very mathematical audience, so we'll see. So the goal of the talk is to explain how scattering amplitudes of a cousin of QCD are correlators of an interesting vertex algebra. So this is like, so what we're doing is closely related to the celestial holography program developed by Andy Strominger and his collaborators. Natalie and I are kind of taking a slightly different perspective on this, and our methods go via twistor space. Now, QCD is, of course, incredibly complicated, really intractable. So what we're really going to be studying is the self-dual limit of the Yang-Mills theory, and this is something much simpler. So if you remember, as I'm sure everybody does, this being a mathematical physics seminar, the Yang-Mills Lagrangian, very familiar, trace f with star f. So the self-dual Yang-Mills Lagrangian has this form. So there'd be a comma there. It's trace b wedge fa minus being the anti-self-dual part of the curvature. And b is a new field, it's an anti-self-dual 2 form, adjoint valued. So the self-dual Yang-Mills Lagrangian and the ordinary Yang-Mills are related in the following way. We can add to self-dual Yang-Mills this term here, g Yang-Mills squared trace b squared. And if we do this, then the two theories become equivalent in perturbation theory. Now, classically, this is very easy to see. All we do is we do the field redefinition like this. That should be fa minus. And once we do this field redefinition, we get trace b squared like this. And this part drops out. And f minus wedge f minus is up to the topological term, the same as f wedge star f. Because of the topological term, this is only an equivalence in perturbation theory. Basically, nothing is understood non-perturbatively, but you can see that from this classical analysis, the self-dual theory, once you deform it in this way, should be related to the Yang-Mills Lagrangian with a very large theta angle. But okay, we don't really understand that. Now, why is self-dual Yang-Mills interesting? So firstly, it's interesting because it's much easier than full Yang-Mills. So full Yang-Mills as a quantum field theory is incredibly difficult. People have done kind of heroic computations to 5 or 6 loops, but nothing exact is known. So self-dual Yang-Mills is not much simpler. Firstly, it's a CFT. Full Yang-Mills theory has a beta function, famously computed by the two Veltman and friends. If one is interested in scattering amplitudes, self-dual Yang-Mills has only one loop scattering amplitudes. It has no tree-level amplitudes, no 2-loop and higher amplitudes. And these are also, the one-loop amplitudes are very simple. There's an explicit expression computed by Malin 30 years ago. And it's a simple rational function. Any computation you would do in self-dual Yang-Mills, the Feynman diagram expansion terminates. But the real interest in it is that self-dual Yang-Mills captures some leading order behavior of full Yang-Mills. For instance, if I wanted to, say, compute the correlation functions in full Yang-Mills of some insertions of the curvature tensor at various points, well, because of this, the way this field redefinition works, or b squared becomes 1 over g squared f minus squared, so it's g to the 4th. Because of the way the field redefinition works, computing this quantity here in full Yang-Mills, well, if I rewrite full Yang-Mills in the first order formulation, you see it matches the correlator in self-dual Yang-Mills plus high order terms. So the lowest order term appears in this computation at order g to the 4n, and it is a correlator in self-dual Yang-Mills. This correlator is not a trivial thing. I mean, I don't know what it is. It's given by some kind of high loop Feynman diagram. But what we're seeing is that the leading order term is captured by self-dual Yang-Mills. Now, many people have looked at self-dual Yang-Mills, and I think it's kind of a dream of many people that perhaps it is a completely solvable theory. So there's a paper of Losev, which suggests that maybe self-dual Yang-Mills is the simplest 4D CFT, and which I more or less agree with. Now, our interest is going to be in the scattering amplitudes of self-dual Yang-Mills. Or rather, let me say that better. Our interest is we want to understand something about the scattering amplitudes of QCD, so the scattering amplitudes of full Yang-Mills. So how would they be encoded in self-dual Yang-Mills? So the way it works, so the full Yang-Mills theory is self-dual Yang-Mills plus this operator. So if I wanted to do a computation in the full theory, I would put this operator at 1 point. I would put this operator at 2 points and integrate over the positions. So I'm just bringing down the exponential. So this tells us that the scattering amplitudes in full Yang-Mills theory are obtained by considering scattering amplitudes in the self-dual theory in the presence of an operator. So let's look at this one. So for instance, if I consider the scattering amplitudes of self-dual Yang-Mills in the presence of one copy of trace b squared, let me draw a trace b squared like this kind of thing. as a little cross. This is something that takes in two negative velocity particles. The propagator goes from plus to minus. So you can convince yourself by playing around with diagrams like this. I think I did a new slide. That's better. So if we take self-dual Yang-Mills plus trace B squared form factors, it computes tree level amplitudes with minus, minus, plus, plus velocities, one loop, minus, plus, plus, and two loop, plus, plus, plus. Okay, so this is just to convince you that these form factors, which are the scattering amplitudes in the presence of an operator, really do, of self-dual Yang-Mills, really do tell you something really interesting about the full theory. Okay. And these are going to be the objects of interest for us. So any questions?
Kevin, if I may, so I'm not sure if I understand the notation, the diagrammatic notation. So the cross is, how should I understand it? Well,
I'll get a new page and make it a bit bigger.
Yeah, so I would like to see it with the diagrams better, I think.
Okay. Okay, so self-dual Yang-Mills, it has a vertex which comes from BAA. And the way you should think of it, B corresponds to negative velocity, and A corresponds to positive velocity. This is because the equations of motion say that FA minus equals 0, so that only the positive velocity part survives. So the vertex is a plus, plus, minus vertex. Like that.
I see. So you have two plus lines incoming and one minus. Okay.
So the propagator is minus plus because it comes from BDA. This is trace B squared. So since B is negative velocity, this is a new minus, minus vertex. And since I'm putting it at some point, I'm not going to integrate over the position of this vertex. So we see that the tree level amplitudes in the presence of trace B squared, what do they look like? So I'll have this thing minus, and this turns into a plus with the propagator. And the vertex is plus, plus, minus. So that'll give me a minus. Maybe that might go off to a plus, plus, minus. Same thing over here. So at tree level, we have two minus external lines, no matter what we do, and any number of plus. Now, if we wanted to do one loop, we could contract a plus and a minus, and we'd lose a minus. And if we wanted to do two loops, we contract another plus and a minus, and it would be all plus.
Okay, yeah, that clarifies it. Okay, thank you.
And what about Faddeev-Popov ghosts?
Right. So, yeah, I didn't want to get into that too much, but one, the right way to treat this is, the BV formalism with, ghosts and anti-fields. So then B would really live, so the fields in BV, you'd have like omega 2 minus, I'm writing the linearized BRSG operator. Here's the ghost. And the whole complex looks like this. And then so this piece here is the antifield of the gauge field. So there'll be a term in the propagator which looks like antifield of the gauge field times the ghost. So you should include that. And we still have the same diagrammatic form. This whole piece, which includes B, antifield to the gauge field, antifield to the ghost, is treated as minus. This other piece is treated as plus. But then we still have the same form with the plus plus minus vertex and the minus plus propagator. Okay, that answer your question?
Yes, thank you.
Okay. So I want to explain the formalism that people in the amplitudes literature use to describe, they compute these expressions and they write down the answers in a very compact form. And I found it a little difficult to understand when I first tried to learn this stuff. So I thought it might help to explain their notation. So we start off with some very simple algebra. We're going to look at complexified momenta, P in C4. Now, as a representation of spin 4, the vector representation is a tensor product of the two spin representations. And the null vectors are the decomposable tensors. So therefore, you can write the set of null vectors is this quotient of S plus times S minus modulo C star. In other words, if we introduce Penrose's notation for spinners with dotted and undotted indices, a null momentum can be written as a product of two spinners, or lambda lambda tilde are in the two spin representations. Now, okay, so this tells us that for a scalar field theory, to specify an Onshell state is to specify two spinors up to scale. But the same thing turns out to be true for gauge theories. So let me explain this briefly. So Onshell states are, of course, solutions of the equations of motion. But for a gauge theory, we should really take them up to gauge equivalence or maybe choose a gauge. And we might as well describe the data of the state in terms of the gauge invariant quantity, dA, which is in this first order formulation, dA would be like this, dA comma B, where dA is self-dual two form. But we can parameterize on-shell self-dual and anti-self-dual two forms by the same data. So there's the following trick. That the positivelicity one, so the trick is that the space of self-dual two forms is the symmetric square of the spin representation. And anti-self-dual two forms is the symmetric square of the other spin representation. So given a pair of spinners, I build a state by this expression. Here, what was that? Is the wrong something? Sorry. Here, I'm just looking at, that's really just e to the px, where p is built from my two spinners. And then the two form part is just built by the square of the spinners I've chosen. And the same for the negative velocity states. Okay. So this is just some compact notation, or given two spinners, I can build a positive or a negative velocity state. And then in this notation, scattering amplitudes and also form factors. There are functions which take n pairs of spinners like this, 5 end states. And to take into account the color factor, they'll produce some element of the dual of the Lie algebra to the nth tensor power. Now, typically, if one wants to look at a high loop amplitude, or even a complicated one loop amplitude, these are very complicated things. They're transcendental, there's polylogarithms appearing. But the things we're going to find in this talk are all rational functions. Now, to describe these particular rational functions, let me write some basic spin 4 invariant functions of my spinners. I have spinners lambda I, lambda j. I can take their inner product because the spin representations are both equipped with an antisymmetric pairing. So the angle brackets ij, here are 5 n particles, I, j, 1 from 1 to n. The angle brackets are just the inner products of the lambdas, and the square brackets are the inner products of the lambda tildes. So typically in the amplitudes literature, the game is then, we've specified our states. Each state is specified by a pair of spinners. And then the amplitude is going to be expressed in terms of these guys, which are functions on my spinners. And here's the classic formula from the late 80s. Park and Taylor computed the tree-level amplitudes with 2 negative velocity and arbitrary number of positive. And they found this really nice expression. Okay, any questions about this? So I'm not sure how familiar people are with this, but.
What's the T in that formula?
T is an element of the Lie algebra. Quite at the top. T is an element of the Lie algebra. So maybe we have an SUN gauge theory. This is how we contract the color indices.
And the gauge algebra is any compact Lie group?
Yes, this expression is true for any compact Lie group, yes. Well, for tree level and one loop amplitudes, the way one contracts the color indices is kind of the same for any Lie group. So they typically just leave that part off. That part is pretty simple, although it's more important at higher loops. Yeah. So now I want to turn to discussing a little bit about the CFT aspects. So our lambdas and lambda tildes there's some scaling ambiguity because if I multiply lambda by an element of C star and lambda tilde by the opposite element, the momentum is the same. So I might as well take my lambdas to be in P1 instead of in a 2-dimensional space. And then, so Stroman et al. In their work on celestial orography suggest that maybe we should think that these amplitudes are really a CFT. They're really like the correlators of a 2-dimensional CFT on a CP1, where at least from my perspective, they might think a little differently. The CP1 is just the projectivization of the vector space where the lambdas live. The reason it seems like this might be a CFT is that if you look at the formulas, they look really like correlators of the CFT. So let me explain this with the product Taylor identity you just saw in the last slide.
Kevin, can I have a question here? In this idea of celestial holography, people usually think about infrared degrees of freedom, so sort of long range aspects of the theory. Is this also happening here? I mean, are you, so I don't see it at the moment. So is this supposed to, the CFT, should it come from the theory at infinity, or is that not, it doesn't go as far?
We don't see it yet.
Mm-hmm.
So what we'll find is that, the natural basis for the states of the CFT are not the exponentiated
Mm-hmm.
states, they're rather the expansion in polynomials. So these are the soft modes.
Right, yes. Mm-hmm.
So I think that's the connection.
Okay, so but there would be soft modes in your gauge theory. I don't see where the sort of long range interactions come in, because I usually associate it with things like QED or gravity, where you really have long range interaction. But here, I don't.
I mean, because we're doing perturbative gauge theory, we're not seeing things like confinement. Right? Like if you were a real phenomenologist, you would say, "What are you talking about? You can't really scatter gluons anyway. You don't see gluons; they're too massive." But that's a non-perturbative effect, which we're not seeing here.
I see. Well, I'm in the Particle Physics Institute right now, so should but I should ask this question. Okay.
Yeah.
All right, but you expect that this is actually a connection to soft modes?
Yes. Let me see. So basically, like we have these exponentiated momenta, our usual states, and the amplitudes we're seeing, they only depend on a finite number of derivatives in X. So we're only seeing the first couple of terms in the Taylor expansion with these particular amplitudes.
Right. Mm-hmm.
So maybe like for us, we have this. It's important that we're dealing with a form factor. So there's some special point, the origin, which I'm inputting this operator trace p squared.
Mm-hmm.
And then the amplitude we're seeing only depend on the finite number of Taylor terms expanded near that point.
All right.
So that's where we're seeing that fact that it's really, we're just detecting soft modes.
Okay.
But yeah. I mean, I feel like there's a lot of, I wish I understood the approach of Strominger and so on better. Like we do things from a twistor perspective and we find everything is so similar, but I don't really understand the details of how they do things.
That's intriguing, actually. That's very intriguing. So I think, yeah, one should definitely understand this better.
But anyway, so let me explain this formula. I think this formula is kind of striking. Let's do the following. Let's just write lambda as 1z because it's in a projective space. And then we take the Park-Taylor formula, rewrite it in this way. And you look, in the denominator, you have lambda I, lambda j is ci minus cj. So in the denominator, you clearly have the first order poles you're familiar with from a 2D chiral CFT. So this observation was made by Nair in the 80s, which turned out to be an important observation and fed into later developments. Okay, so what I want to So what I want to explain is how to build a chiral algebra whose correlators will give you amplitudes like this. So the precise statement is, at tree level, we're going to move on to loop level later. And there are some difficulties. But at tree level, the statement is that there is a vertex algebra. So that's just the thing you have when you have a 2D chiral CFT, and the OPEs are meromorphic functions. And it has the feature that all form factors of self-dual Yang-Mills, so remember, a form factor is a scattering amplitude in the presence of a local operator, are the same thing as all correlation functions of the vertex algebra. So let me describe the vertex algebra. It's extremely simple. So I take my Lie algebra plus its dual, and we have things set up so that the bracket of two elements of the dual vanishes. And then the vertex algebra is simply the Cas-Moody from my Lie algebra plus its dual adjoin two variables, v1, v2. So if we unpack this, we find that there's two towers of currents, J's, J tildes, each of which depend on a pair of indices m and n, which are integers. J's of spin 1 minus n plus n over 2, J tildes of spin minus 1 minus n plus n over 2. So we notice that the vertex algebra has lots of things of negative spin, which is a little unusual. And then it has these very simple OPEs. JJ OPEs picks up a first order pole, JJ tilde, first order pole, and J tilde has no pole. Okay, so why would we want to do this? So I want to identify form factors with correlation functions. Now, the ingredients of a form factor, an endpoint form factor, I need to give you n states. Whereas to give a correlation function in the vertex algebra, I need to give you n elements of the vertex algebra. So we're going to need to identify the data of states, the elements of the vertex algebra. And this is how it works. So the generators of the vacuum module are in one-to-one correspondence with the states of the gauge theory. So here's how we see it. To give a state, I need to give you two spinners. One of the spinners, lambda, encodes where on CP1 I am. For the other, lambda tilde, well, I arrange my generators into my vertex algebra into a series like this, with the lambda tilde spinners appearing in the series. And the same for the J tildes, lambda tilde spinners appearing there. And the way we match things up is that psi plus positive velocity states is the generating function of the J's at that particular point in CP1 corresponding to lambda. And the negative velocity corresponds to the J tildes. So we notice under this correspondence, JMN corresponds to a solving mode. So because it's just determined this sum, it's a state which is a polynomial. So I hope that answers Kazia's question.
That clarifies it somehow, yes. Yes. Yes.
Okay, so this is the basic part. So to give a form factor, we need to give a bunch of states and a local operator. So where is the local operator? So there's another piece of things which appears. So here, I'm unfortunately realized that this slide was aimed a little bit at a math audience. So I think it might be a little technical. Or like, he's not technical, use terminology people might not be familiar with. So what happens is that the conformal blocks of the vertex algebra, that's a vector space. The vector space of conformal blocks is isomorphic to the space of local operators. So this is going to be good because if I have a vertex algebra, the vertex algebra isn't really a 2D theory, it's just an algebra. To give correlation functions for vertex algebra, you need to specify a conformal block. And to define a form factor, we need to specify a local operator. So it's really good that these are in the same vector space. So how do you do this? How do you check that conformal blocks are isomorphic to the local operators of the gauge theory? Well, it's really not hard at all if you know the literature. There is a result of Belos and Drinfeld, which tells you how to compute conformal blocks. And if you run that result, you find it's expressed in terms of the double cohomology of twistor space. And then you can apply the Penrose-Moore correspondence, which says double cohomology groups of twistor space give you the fields of self-Julian angles, or the operators of self-Julian angles. So that's it's very easy if you're familiar with the right papers. So why is this good? So let me finally, I'll pause at the end of the slide, ask more questions.
So maybe one question to the twisters. So is this result like the main place where the twisters come in? Or
well,
why twisters?
Right. So we build the vertex algebra, especially at loop level, by taking the twister uplift of self-Julian Mills, which is holomorphic BF theory, and then analyzing it on twister space.
Right, right.
So secretly, twisters are like a black box behind everything.
But how do you know twister? How do you know that twisters is the right thing? So what's the sort of, well, is there some fundamental reason why this is the right structure to look at? I'm trying to understand that.
Well, I think the twisters are not totally essential, right? And you could state everything without mentioning twisters once.
Okay.
You might just have a difficult time proving it.
Right.
But so, I didn't mention twisters to write down the vertex algebra so far. I just give you a formula, and then anybody can go away and read the definition of conformal blocks and just check that conformal blocks are local operators. That's just a statement of mathematical physics that anybody can really check. It just so happens that the slickest proof goes through twistor space, but
Okay, fair. There is a question by Dorothea. So
yeah, hi. I have a fundamental question that is a bit in the direction of what Kaja was asking. I don't understand the philosophy of the program, because usually form factors are introduced to sort of effectively model something that the theory doesn't really predict well. I don't understand what the first principles are that you're using in order to sort of predict the form factors, which in my sort of view of physics are more of an something you would adjust as a model once you've done experiments. So I don't understand. I'm sorry, maybe I should have listened more carefully, but I don't understand the philosophy how you want to construct form factors, sort of from first principles.
I mean, we're not going to be. I think everything we're doing is probably much more formal than what you're thinking, right? So a gauge theory has many observables. Form factors are one of them, and perhaps they're not the most physically relevant observable or the most relevant to experiment. But if you're just interested in mathematically studying gauge theory, it's a perfectly fine thing to study for its own sake.
Yeah, I agree, but I don't understand the physical principles that lead you, for instance, using twisters.
Oh, well, okay, so using twisters, let's think about it like this. If we have a theory on twistor space, a local field theory on twistor space, never has any scattering. The reason is a state on R4, you can lift it to something on twistor space, which lives along a copy of R4 in twistor space. So like the twistor space looks like CP1 times R4. My state can be localized at a point Z times R4. And then for different values of Z, these just don't talk to each other. So there's no scattering. So for any local theory in twistor space, to get any interesting scattering thing, you have to have something, a blob of something on a CP1, and that's the local operator, which gives you the form factor.
Thanks.
Right. Okay.
Yeah, I think that might be an interesting topic to discuss further. But yeah, let's carry on.
Okay, I mean, I realize maybe I give my talk backwards by like hiding everything about twisters in the seminar.
No, yeah, I will come back to this after the talk, I think. Okay.
Okay, so let me see. So what do we have so far? So form factors, these require two things: an operator and end states. Correlation functions, these require a conformal block and n vertex algebra elements. So what we've seen so far is that they depend on the same data. Conformal blocks are operators, and states are elements of the vertex algebra. This obscures this thing. So the result is, okay, I take my operator of my gauge theory, I take the corresponding form factor. That's a function of my lambdas and lambda tildes. On the other hand, I reinterpret my operator as a conformal block, and I take the correlation functions, and these are the same. So the tree-level punchline is that all tree-level form factors of soft 9 mils, you can just compute them in this very simple way by looking at correlation functions of the vertex algebra. So let me give you a simple example, which will allow you to go away and prove this famous Park-Taylor formula, which, it's not a big deal because it's been proved in a million different ways from many different perspectives, but it's a good example to understand. Okay, so the operator trace b squared, it's some local operator in the gauge theory. So it gives you some correlation function, some conformal block. To figure out what it is, typically, if the correlation function of n operators in my vertex algebra, it's going to be determined inductively by what happens for a small number of operators by the OBE. So the seed, in this case, because trace b squared is an operator of length 2, involves 2 fundamental fields, the seed is what it does to 2 insertions. And it's not hard to convince yourself that the insertions of 2 j tildes gives you this expression. That's just by symmetry reasons. And now you can go away and compute what it does to an arbitrary number of insertions, and you find this formula, and it's the Park-Taylor formula. So let me explain it for 3. Just very quickly. So for example, I have j tilde so our vertex algebra says there's a pole when that hits that, and there's another pole when that hits that. There's no poles when 2 j tildes hit each other. So this will be looks like this, j tilde times 1 over z2 minus z3 minus 1 over c1 minus c3. So if you work it out, that's, will give you pretty quickly c1 minus c2 cubed over c1 minus c3, c2 minus c3, which is the correct amplitude. So the rest of them are determined in a similar way. So this is kind of fun because, you know, it tells you that there's a simple Park-Taylor-like formula for any form factor. Okay. So I want to move on to a discussion of what happens at the quantum level. Unless there's any questions. Okay. So what we see here, tree level, this nice story, correlators of the vertex algebra are the same thing as form factors of the gauge theory. So can this be true with the quantum level? So Guevara, Himich, Pate, and Strominger analyzed this question for amplitudes. And they look at states of positive velocity, and they find the answer is yes. So it's pretty nice, and they do it for gravity too, which is much harder. But if we consider all states, both positive and negative velocity, the answer is no. I mean, we're asking slightly different questions here, so there's absolutely no contradiction with their work. So one way to see this is, I mentioned that self-July Mills is a CFT. So like in any other CFT, there can be some non-trivial matrix of anomalous dimensions. I take an operator, which classically has some dimension. At the quantum level, the action of scaling gets quantized in some complicated way, and these operators might mix between each other. So this happens for self-July Mills. We take the operator trace b squared. Classically, it has dimension 4. L is a length scale. But at the quantum level, it does not. The matrix of anomalous dimensions takes this funny upper triangular form. I mentioned that self-July Mills is non-unitary. And here we're seeing that the Hamiltonian in radial quantization is an upper triangular matrix. So yes, it's non-unitary. Now, this seems like it cannot happen because in any, we have a vertex algebra with some flavor symmetry, some action from grading by C star, and then we want to quantize it so that the grading involves logarithms. That just seems nuts. It seems like it can't happen. But a better way to say it can't happen at the quantum level is by going and examining the QCD literature. So I could have guessed what my vertex algebra had to look like by staring at the Park-Taylor formula and looking at the poles. That would have told me what the OBEs were. That's what Nair did. Now we can try to do something similar in one loop. And fortunately, there's these lovely papers from the 90s by Byrne, Dixon, Kosover, and Malin, who computed many one-loop QCD amplitudes. And they also computed singularities in these amplitudes when two states become collinear. And you can look at their expressions and say, okay, which ones will come from self-Joule-Yang-Mills theory, and how will that correct the vertex algebra? So you look at their expressions, you can convince yourself that one of their expressions looks like this, that two states of my vertex algebra must acquire a new OBE with a 1 over z squared term. So C is some particular constant, it's like 1 over 96 pi squared. Like this expression is, this OB is literally just lifted from their papers and recast into a vertex algebra OB. Okay, so does this define a new vertex algebra? No, it does not. The reason is vertex algebras have to be associative. You can't just define your OB willy-nilly. There's an associativity relation. The associativity relation tells us that this expression here, this should be kind of meromorphic in a function of two variables. Which means that if I do certain contour integrals, this expression, there's three contour integrals to look like this. So one of them. That's the other, where red and blue means Z and W. The third one looks like this. Associativity says that the linear combination of these three contour integrals is 0, but you just compute it and it's not. Okay, so it seems like we're doomed, but we are not doomed. And we can fix these problems. Okay, before I explain how to fix the problems, any questions?
No, I think we're good.
Okay. So for us, I've kind of hidden twistor space, but everything for us comes from certain gauge anomaly in twistor space. And the gauge anomaly is associated to this gauge invariant polynomial, the trace in the adjoint of x to the fourth. So there's two ways to cancel the anomaly. I could add on some matter so that this identity holds. Well, if I add on matter in the adjoint representation, that will always work. I will give you a supersymmetric theory. So this problem won't occur with the supersymmetric theory. But there's other examples too. I can carefully choose my matter so that this holds. So like SL2, and this representation is referred to as NF equals 8. Alternatively, I can assume that trace of x to the fourth factors as a square. And this holds if G is SL2, SL3, SO8 are an exceptional algebra. And then we can add on a new field which cancels the anomaly. And this new field is an axion. So it has a funny fourth order term here. And it couples to the topological term, the gauge field. And there's some very particular constant in this coupling. So the theorem is that in either of these contexts, this whole story works at the quantum level. So I should call this conformal box. So there is a vertex algebra which deforms an extension of the vertex algebra I wrote down originally. I extend it by adding on these new fields, whose conformal blocks are local operators, and such that correlation functions are form factors. So this vertex algebra is, it's more complicated. So it's a kind of quantized enveloping algebra. So I'll think about it to go a little faster. So I don't expect people will follow everything or anything really. So what we have to do is we add on 2 more towers. These correspond to the field rho. We get 2 towers because, normally every field will give you 1 tower of generators, but there are 2 because rho satisfies a 4th order equation, which can be thought of as 2 fields satisfying a 2nd order equation. And then our twistor perspective gives us some OBEs, which we don't need to read. And then the OBEs between J and J tilde get deformed in a certain way. So one of the terms involves a normally ordered product. And this other term is the same as the expression discovered by Byrne, Dixon, Costello in their study of 1-loop QCD splitting amplitudes. So what we find is this is the only way, these corrections are the only possible corrections to the OBE for symmetry reasons. And if you add on these corrections and you add on our new fields E and F, it is associative, and the problem we had before disappears. The proof that you just calculate, this is my idea of fun. It might not be everybody else's idea of fun, but you just do a ton of algebra and you find everything cancels in this kind of amusing way. Okay, so one fun feature is that if you're really careful with matching the usual normalization of states to the normalization of the generators, the vertex algebra, you find the same coefficient that Byrne, Dixon, and Costello did in their study of splitting amplitudes. That's it. So by pure algebra, we derive this same coefficient. So I thought that was quite fun. What else? This is kind of aimed at more math people, so we can put that. Okay, so the point of all this is that now we have some way of doing loop level computations in form factors by using a vertex algebra. So let me quickly explain. I'd like 5 minutes left, Kazuya, right? Or no, 0 minutes?
About, yes. Okay.
So maybe this should be my last slide then. Okay. So there was this really nice calculation by G. Malin from about 95. We calculated the 1-loop all plus amplitudes. And you find this beautiful rational function. So we want to see as a test, the whole story is like, can you reproduce this as a correlator of the vertex algebra? Well, you can, but it's a little trickier than the one for the Park-Taylor amplitude. So what you have to do, well, this amplitude here is an amplitude in the self-dual period, so we don't need trace b squared. But instead, we need to add on some operator which removes the axion. So the thing we're going to do is add on this operator, or subtract it, because if I subtract that from the Lagrangian, the axion doesn't propagate. So we would expect that the form factors for this operator reproduce Malin's expression. Now we translate that into the vertex algebra language. the correlators of the vertex algebra should reproduce Magellan's expression. And you just go and compute it, and it does.
Excuse me, could you recall what are the square brackets and angular brackets?
Right, so the angle brackets is like epsilon ij, lambda I, lambda j, or and God, I wrote this terribly. So it's the inner product of lambda I, lambda j. It's the inner product of lambda tilde I, lambda tilde j. Where lambda I and lambda j are the spinors of positive or negative velocity, and they use this notation where your amplitude is described, like a state is described by a pair of spinors.
Thank you.
Maybe very last slide. So in theory, our results should go further. So we should be able to compute one loop amplitudes with one negative and n positive velocity. The difficulty is, well, these were computed by the same group of people, but the answers are incredibly complicated. So from our story, we do the same thing, and our answer is really easy. So for our story to work, if we introduce the axion, or if we're careful about our gauge group and matter, these two expressions, one at the bottom and the top, must be the same. So there must be some miraculous cancellation happening in these complicated expressions. So I'm kind of working on that, and it's really hard. But it's just, a very concrete consequence of the existence of the vertex algebra is that these one loop and even two loop expressions will be much simpler. Okay, so I think I should stop there, and thanks everybody for your patience. And I'm sorry I didn't get to twistors, but
this we can leave for the discussion. So thank you, Kevin, for the nice talk.
Thank you, Kaja.
So there were many questions already during the talk, but now it's the time for more. So please go ahead and unmute yourself if you have any questions, or you can also post on the chat. Questions? Well, if there are no immediate questions, I will ask further about twistors then. So this is something I'm trying to understand sort of from a more geometrical perspective. Yeah, can you say something more about, well, is there any geometrical interpretation about what's going on there? Because somehow you gave us the algebraic picture, but I was wondering if there is some geometrical intuition behind it as well. So yeah, I mean, I've seen kind of, I could follow the manipulations, but I don't see why things work so miraculously, so to say.
Yeah, let's see. So the way I want to think about it is, once you have a local theory on twistor space, you can build a vertex algebra. But the way to build a vertex algebra involves this kind of algebraic thing we call conjugal duality.
Okay.
So the vertex algebra is like, I have a theory on twistor space. Twistor space is, O1 squared to CP1. And I can consider, can I couple my theory to some 2D CFT living there? And the vertex algebra we're building is like the universal vertex algebra that can be coupled. So the issue, like why things don't work unless you're careful about the representation or introduce this weird field, that's not like, on twistor space, holomorphic BF theory has this anomaly. And you need to do something to cancel that anomaly to get a nice theory on twistor space.
Right. Yeah.
So that's kind of the main point.
Ah, okay. So that's okay. So that's the sort of twistor space anomaly. Okay. And another question would be about dimensions. So does this generalize to different dimensional story? Because I mean, usually, well, you do vertex operator algebras in 2 dimensions. This story is, I think, 4-dimensional intrinsically, right?
Well, there's also you could do the same thing on mini twistor space. And you could also do the same thing for 4D Chern-Simons theory, which would relate to 2-dimensional integrable field theories. And in each case, there will be some vertex algebra. As you go down in dimension, the vertex algebras get simpler and simpler.
I see. Okay, and the underlying trick is always causal duality, or is it just?
Yeah, it's always exactly. It's always you look at the universal thing you can stick along that CP1.
Okay. Well, that's helpful, at least for me. Okay. Any other questions, comments?
I have a question. So, how useful are these results for practitioners? So, can they? I mean, I understand that this leads to some to a computation of some gluon amplitudes, and can this be used in real QCD? And so, which information is useful?
Well, I don't think anything we've said is useful yet. I mean, I don't. Like, there's all these really great people studying amplitudes just directly, and they've done a bunch of great computations, and we haven't. We're kind of catching up with them, so we haven't done any computations that they don't know about yet. But I'm hoping that we'll be able to do something a little different than them. But even so, I don't. Yeah, I mean, I personally just want to understand these structures on their own sake. I suspect, as I mentioned earlier, that one's going to run into the issue that you never see gluons hanging around by themselves. So you can't really compute scattering amplitudes of just gluons in the real world.
Yeah. So, but for instance, can you couple matter fermions, for instance,
yes,
to this self-dual Young-Mills, and can you compute amplitudes then?
Yes, you can. You can compute fermions, and it's things work really nicely with SL2 and NF equals 8, for instance, and then you can compute amplitudes there. Yes, but still, I would say that I currently do not have not done any computations that were not already done 25 years ago by other people.
Thank you.
Thank you for the question, Jan. Okay, any more questions? I'm looking, is there anything on the chat? No, no raised hands. Okay, so maybe we can close the official part of the seminar, and let's thank Kevin again.
Thanks, Kasia.
For coming.